Well, hello and welcome to this short presentation on dry gas basics for turbo compressors, for centrifugal compressors. We'll be looking at the basic operation of a dry gas seal, where they're used, the different terms used when dealing with dry gas seals, and also the control and monitoring systems and separation seals. My name is Phil Manning. I'm the Senior Technical Product Trainer for John Crane. I've been with the company just over 31 years, starting in 1989 as a test and commissioning engineer working in the Gas Seal Group. The Gas Seal Group is based in Slough, just west of London, and is the centre of excellence for dry gas seals. After working as a test engineer for a few years, I then worked as a product engineer before a long period of time working as a field service engineer. In my role as a field service engineer, I was working both onshore and offshore, working in various aspects of dry gas seals, from the commissioning and startup to any kind of troubleshooting and general service work, all relating to dry gas seals and dry gas seal related products. In 2008, I joined the training department to use the knowledge and experience I'd gained from working as a field service engineer in a training environment. And now myself and my colleague Keith Bolton are the global trainers for dry gas seals. In addition, I do training on wet seals as well. Now, at the start of our classroom courses and also these online courses, we have a safety moment. Today, we're looking at pressure, and pressure in particular in pipelines. Now, if you go onto a site, whether it's onshore or offshore, for a refinery or a petrochemical plant, there will be a lot of pipe work and it will be under pressure, maybe from liquid, maybe from gas. It can be potentially fatal, and so there are indications showing that the pipe is actually under pressure. Pressure gauges, pressure measuring devices, flow meters, all of these will indicate that there is pressure inside and it needs to be isolated before any work can take place. Today, we're looking at dry gas seals. Dry gas seal pressures are forever increasing, and so the pressure in pipe work is also increasing. And so any work that needs to be carried out on, say, a centrifugal compressor needs to be done in a safe condition. All pressure needs to be released and drained from the compressor and the relating pipe work. So if you're not sure, then you should stop work and ask. Make sure that everything is isolated and that there is no pressure present. Even a small amount of pressure inside the compressor casing can cause the seals to come out very, very suddenly, which could cause injury. So if you're not sure, ask and you'll be safe. With dry gas seals, you're generally dealing with centrifugal compressors. We'll be looking later at the various types of spiral groove systems, unidirectional and bidirectional. This technology of giving a non-contacting operation is now used on not only compressors. It can be used on horizontal shafts for agitators and mixers, high-speed turbo expanders, steam turbines, as well as being used on various wet pump applications. Today, however, we're looking at compressors. And the compressor you can see on the screen here is from a group of companies called Siemens. Siemens have a number of different types of compressors. And what you can see at the moment here is what's referred to as a barrel compressor with a barrel or bundle. This is where the actual compression of the gas takes place. The compressor consists of two main components, the parts which rotate and the parts which are static. And the same will be true as we see with the dry gas seal. We can see that we have two different ends. One end is the non-drive end to the left, and you can see there are bearings, radial bearings and a thrust bearing. The radial bearing is there to support the shaft and comes in two halves, a bottom half and a top half being bolted together. Outboard of this, there is a thrust bearing, typically a thrust disc, which is shrunk onto the shaft with tilting pads either side. At the drive end at the right, there is also a radial bearing, again to support the shaft. The drive end is connected to the drive system, either directly or through a gearbox. Compressors are driven one of three different ways, either using a gas turbine, or a steam turbine, or an electric motor. And this may be with the aid of a gearbox to increase the speed of the driver shaft to the driven shaft. You can see that we have two dry gas seals, one at the non-drive end and one at the drive end. These are between the process, which is where all the impellers and the diffusers are, and the bearings. And so the only way we can tell the condition of a dry gas seal is what goes into the seal and what comes out of the seal, the gas. The compressor operates by being supplied with a gas at a low pressure, which comes in through the suction. It goes through a number of different stages, and as it goes through these stages, it increases its pressure, increases its temperature, its velocity, but there's a decrease in volume. And so the gap gets gradually narrower as it goes from the suction through to the discharge. By the time it comes out of the discharge, it's at a high pressure, high temperature, high flow rate, and this pressure is generally what we would use to supply our dry gas seal. We'll explain a little bit later. So this type of compressor is used for generally medium pressures, but there are other types that are still working on the same principle, but for lower pressures. Take, for instance, this one here. This is one from a company or a group of companies called MAN Turbo. This is in one of their factories in Germany, and you can see that the casing has two halves. We can see the bottom half, and there's also a top half. We can also clearly see that there's the rotor assembly, including the dry gas seal, which has this yellow plate, and the bearings. What is happening here is that the rotor assembly, the complete rotor assembly, has been lowered down into the bottom half of the casing and is resting on labyrinths. There are labyrinths between the various different stages of compression. And at this point, they're checking the clearance. This will allow for a small amount of gas to pass between the various different stages. If the gap is too large, then they would reduce the amount of efficiency of the compressor. If the gap is too small, then it may result in vibration from contact. The other check they're doing is they're checking the axial position of the shaft relative to the casing. This is very important, again, for the efficiency of the compressor, also for setting up the thrust bearing, and also the positioning of the dry gas seal. Once these have all been established, the rotor assembly will be lifted out of the casing. The shaft will then have the dry gas seals removed and the bearings removed, and it will be lowered back down into the casing. The top half of the casing will be then lowered down, and it will be bolted in position using these large studs that you can see all the way around. Then the dry gas seal can be installed and bearings. Now this type of arrangement is for lower pressures. If it went to a higher pressure, there would be leakage through the midline split. So that's two types of compressors which would use dry gas seals. There is actually a third, and the third one is referred to as a bell casing. The bell casing is generally used for re-injection of gas. So we have our middle horizontal split. We have our barrel compressor, which is by far the most popular type. And then we have the bell casing. You can see there's a very large wall thickness for factors of safety. So this one is used purely for re-injection duties. But all of these, together with other types of compressors, have their own individual applications, as you can see from this graph. It depends on pressure. It also depends on the volume as well. So we have the high pressure system here, with the bell casing, but we might have a pipeliner compressor. A pipeliner is where the gas comes in at a pipeline station. There's a small amount of compression on the gas to take it to the next pipeline station, which would be identical. There are also other types of machines which also would use dry gas seals. Overhung systems, where there's only typically one seal being used, or integrated gear type, which might have a number, 4, 5, or 6 seals might be on one compressor. Now, it may not be that you'd use one compressor for an application. There wouldn't be enough compression of the gas produced by just one single compressor unit, and so you'd need a compression train. The photo you can see has 3 compressors: a low pressure, a medium pressure, and a high pressure or export. To the right, we have a gearbox, and further to the right, we'd have a gas turbine. Now, this arrangement was actually for an application in Alaska, where the gas had to move tremendous distances to reach its destination. The design of these compressors has a drive end seal on the low pressure and a drive end seal at the medium pressure, which are interchangeable. The seals are both running in the same direction and would be tested to the low pressure and the medium pressure. The same would happen with the non-drive end seals at the low pressure and the medium pressure. So it reduces on the number of seals that are actually supplied. However, the bell casing that you can see on the end here has a much higher pressure design. And we'll look at the various different designs as we go through the presentation. Now, the dry gas seal is very versatile. It can be used in a number of different applications, both onshore and offshore, from the extraction process to the actual production. It can also be used in refineries, where different processes are carried out, requiring compressors, therefore requiring some kind of sealing system. They can also be used in petrochemical plants, where ethylene and methanol is produced. Or it may be in another industry altogether. Rather than oil and gas, it may be used in the manufacture of fertilizer, where we use ammonia and urea. A lot of gas is needing to be transported using pipeline systems, or, as you can see from the photo, using a tanker. The gas is transported using pipeline systems with pipeline compression stations. So the gas is transported to the next compression station, where it is boosted before it reaches the next. There are new processes being carried out. LNG and GTL are new processes also requiring dry gas seals. The ship you can see in the photograph is actually transporting LNG, where the natural gas has been liquefied. By taking it down to a very low temperature, the volume has decreased and it's become a liquid, which makes it safe to transport around the world. But what is dry gas seal? Well, dry gas seals, although some people think they're a new concept, have actually been around for about 50 years. The initial dry gas seals were using O-rings, as you can see from the one on the screen. This is a single seal, and we don't sell very many single seals. It tends to be for very safe gases, air, nitrogen, and carbon dioxide. But it gives us an understanding of the various different components and how they work using gas. Now, all seals work with 2 main components, the parts which rotate and the parts which are static, and the dry gas seal is no different. Here we have our seal rotor. The seal rotor consists of a mating ring, sometimes called a seat, and this is typically silicon carbide or tungsten carbide, a very hard material. It's installed inside a sleeve, referred to as a shaft sleeve because it's in contact with the shaft. There's an O-ring around the back of the mating ring to seal off the gas, and there's also an O-ring in the bore to seal off against the shaft. To lock it all in position, we have a locking sleeve. This locking sleeve, as you can see, has screws which are to tighten it all together. Now, this assembly is balanced, and balance is very, very critical when dealing with dry gas seals. Typically, a dry gas seal will run at 10, 15, maybe 20,000 RPM, and so balance becomes very, very important. If it's unbalanced, then it will give high vibration. High vibration could cause damage to the seal, bearings, coupling, and the compressor in general. So it's very important that the seal is balanced. And when doing balancing, you can do one of 2 things. You can either remove material or add material. We remove material from the end of the locking sleeve and from the end of the shaft sleeve. So every time the seal goes on and off the shaft, it's within the balance quality. The other part of the seal is the seal stator. This consists of the primary ring, sometimes referred to as the face, an O-ring, a thrust ring, a metal disc, multiple springs, a retainer, and a face retainer. This is all assembled together. The diameter here is referred to as the balance diameter. It sets the size of the dry gas seal. We don't refer to the seals by the shaft diameter, but by this balance diameter which this O-ring is sealing against. I mentioned there are springs, multiple springs. The number of springs would depend on the application and the size of the seal. The larger the seal, the more springs necessary to create the closing force. The face, the primary ring, is held in position using this face retainer. But you can see that the O-ring position is halfway along the balance diameter. This is the nominal position. And in order to achieve this nominal position, it may be necessary or required to use shims. So we have a shim here and we have a shim here. This gives the correct actual position of the seal. Some manufacturers may have shims on the shaft to get the seal rotor in the right position relative to the stator. Now, if we look at the shroud around the outside diameter of the mating ring, we can see it's there for two reasons. Firstly, it's there to contain the mating ring should it fail. If a mating ring fails, it wants to fly out with centrifugal action. The idea of the shroud is there to catch it, so there are no parts coming off causing any secondary or tertiary damage. But the shroud is there for another reason. It's to create drive, a positive drive on the outside diameter of the mating ring. Now, I mentioned that we use tungsten carbide and silicon carbide. These two materials have different properties. The two photos at the top on the left-hand side show silicon carbide. Silicon carbide is very hard, yet it's very brittle. It's easily chipped. If there's a point contact, then it will easily get damaged. So we have this notch design for silicon carbide, and the photo on the right-hand side shows how it locates with the outside of the shroud. There are two notches diametrically opposite, creating the drive. As I said, silicon carbide will be damaged from a point contact, so we have a surface contact, which creates the drive. The bottom two photos on the left-hand side show tungsten carbide. Tungsten carbide is very tough, very strong, and doesn't suffer from the problems of being brittle. And so we have flats rather than notches, and so it's driven off a point rather than a surface. If we look at the primary ring, we see that it's inside the bore of the retainer, and there are profile milled pins. These pins are equally spaced around the inside, as you can see here. Originally they were pins, but now they're profile milled. And there's always three, or a number divisible by three. These locate with the little notches, the little cutouts that you can see on the outside diameter of the primary ring. And again, they're there for two reasons. One is to guide the primary ring back and forth, and secondly, to prevent the primary ring from rotating. On a dry gas seal, the primary ring is always a static component, and the mating ring is always the rotating component. So here we have the two together. We have the mating ring or seat, and we have the primary ring or face. You can see now we've introduced the spiral grooves. These spiral grooves are unidirectional. They only work in one direction, either clockwise or counterclockwise. We'll see in a moment that there is also a bidirectional groove which can run just as well in both directions. Between the two, there is a small film. This film is only a matter of microns in size, typically 3 microns. The gas will enter the grooves and create a pressure. This pressure will push the carbon face away, but the springs will try and close it. So there's constant readjustment of the gap. This gas that's being supplied needs to be clean and dry at the correct temperature and pressure, and it needs to be continuously supplied before you start up, so a static condition, whilst it's running, dynamic condition, and also after you've shut down, a hot static condition. This means that the mating ring and the primary ring are not together. They only separate when the pressure becomes about 6 bar. So once the pressure gets to 6 bar, this will overcome the spring force and create a lift. So you get a small amount of leakage. Whilst it's in operation, you will also get the lift, but it'll be caused by pressure and rotation. So let's have a look at the grooves a little bit more in depth. Here's a unidirectional groove. The groove, as you can see, is made up of 3 arcs, one here, and one here. If it's in a static condition, the gas would enter the groove, and when it reaches the end of the groove, the root of the groove, it builds up a pressure, which creates the lift and gives you your non-contacting operation. Once it's dynamic, you can see the rotation is clockwise, the gas is drawn into the groove, and again creates the lift. So lift can be created by hydrostatic or hydrodynamic forces. Now this is unidirectional, and it could be clockwise or counterclockwise, and all seals until the mid-1990s were unidirectional seals. Then there was a request to have a bidirectional seal. The reason for the bidirectional seal, which you can see on the screen now, was for the possibility of running in reverse. With the unidirectional seal, if it's running in reverse, running backwards in effect, then rather than creating a lift, it will bring the surfaces together, which will create contact, heat generation, and possible damage. So the bidirectional seal was developed so that it could run in both the clockwise and counterclockwise direction with no problem at all. Both seals, the drive end seal and the non-drive end seal, would be identical, would be interchangeable. The way this seal operates is the gas enters this slightly deeper groove here and goes into these 2 wings. This creates the gas film, and it is able to give you the correct amount of leakage. Both directions will give the same leakage in each case. Now there are some slight differences between the unidirectional groove and the bidirectional groove, one of which is the actual lift-off speed. The lift-off speed for the AT, the O-ring seal with unidirectional grooves, is 2.3 meters per second, whereas the bidirectional seal of the same type, but only the grooves being different, is 3.5 meters per second. There are also issues when we reach higher speeds. Once you reach 18,000 RPM, then this is pretty much the limit of the bidirectional seal. One reason is that there are less grooves using a bidirectional seal, and high-speed seals tend to work with very small diameters, and so the number of grooves is an issue. So a unidirectional seal will always be the first choice, with a bidirectional seal as an option to the customer. So going back to our single seal again, we can see now where the gas is entering and where the gas is coming out. Now, typically on a dry gas seal, the gas that we use as our seal gas, our primary seal gas, is actually the process gas that's come from the casing. But once it comes out of the compressor casing, it's dirty. It's high temperature, which is good. It's high pressure, which is okay, but it's dirty. And so it needs to be filtered to take out all the particles that would actually cause damage to the dry gas seal. So we need to use filtration. And there are various different types of filtration that we can use to remove particles, remove liquids. There are other systems, however, that can be used to remove liquids. Heat tracing is quite popular, but also if you can use a different gas when starting up. You may use warm nitrogen or fuel gas as your startup gas, and then it gets replaced with the process gas when it reaches the correct pressure. So our gas has been filtered and then been injected into the seal at this port. The gas can do one of two things. It can either go back inside the compressor, which the majority of the gas does, and this keeps the dirty gas inside the actual compressor. What we don't want is the dirty gas to come through the labyrinth to cause damage to the various parts of the seal, creating hang-up and damage. The other path that the gas can take is actually through the dry gas seal, and so it comes out as leakage. Now, in order for this seal to work, then the pressure that's been applied to the seal has to be higher than that of the pressure in the process. There's normally a differential pressure of a bar or 2 bar in order for this to happen. So once it's in operation, we're getting a small amount of leakage coming out. As I said, single seals work on very, very safe gases, and this gas could go straight to the atmosphere without causing any issue. But we have to think about the bearings. The bearings are lubricated with lube oil, and we don't want the lube oil to go into the dry gas seal. After all, it is a dry gas seal, so we want no liquids to enter the seal at all. So between the bearings and the dry gas seal, we typically have a labyrinth, which this gas would pass through to prevent any migration of the lube oil. Now the seal you can see here is a type 28AT. 28 is the number that John Crane has given to spiral groove technology seals. And the type 28 is a dry gas seal. The AT that you can see at the top stands for advanced technology. It was the original form of dry gas seal going back to the late 1960s, 70s and 80s. And there's still ATs in the field today. But they have limitations, and the major limitation is on pressure. As you can see from the bottom, the maximum pressure this seal could go up to across one stage is 82 bar dynamic, 123 bar static. Once it exceeds this pressure, then there'll be issues of extrusion. And so if pressures were higher, then it caused problems. And so the seal had to be redesigned to cope with these higher pressure demands. Now, we have a tandem seal, and the tandem seal is by far the most common type of seal being supplied. It's essentially two single seals. So on the right-hand side, we have the process side. On the left-hand side, we have the atmospheric side. Seals can be known by different names. The process side seal, the atmospheric seal, primary seal, secondary seal, inboard, outboard. There is a lot of different terminology used when dealing with dry gas seals that could be a little confusing. But if you understand that the process side seal that we have here is working on high pressure and the atmospheric seal here is working on low pressure, you'll get more of an understanding. Now the inboard seal that we can see here is being pressurized, as we saw with our single, with our filtered process gas, sometimes called the primary seal gas. The leakage that comes through the seal will then go up the primary vent. The primary vent is where we measure the gas, either as a pressure or as a temperature or as a flow or as a differential pressure. This primary vent would lead off to the flare where the gas would be burnt off. But if all the leakage of this seal went up the primary vent and was burnt off, then it would starve this seal of any pressure. And so the only time it would lift was when it reaches the correct dynamic speed. So in the primary vent, there will be some kind of a restriction, an orifice plate, or maybe a needle valve to provide a small amount of pressure necessary to separate the seal for a startup and running conditions. The primary vent, as I said, is how we measure the gas that's coming out. Now, on some primary vents, you would have an alarm and a trip. on a high condition, but also on a low condition. So if the leakage goes down very rapidly to a low alarm, and then to a low alarm, a low trip, then the unit would shut down. Now there's a new standard that's been introduced for dry gas seals. It's the API 692. It's been out now for 2 years. And in this standard, which is purely for dry gas seals and related systems, it states that the secondary vent, which generally would not be measured, needs to have some kind of measuring device as the standard. So you'd be able to check the primary leakage and the secondary leakage whilst it's in operation. Now, if we look at our tandem seal, we can see that it's a much larger seal. It's a longer seal. It has more components. The seal rotor now is much longer. There are 2 mating rings. The shaft sleeve is now longer with more points of contact with the shaft. And there is a spacer sleeve as well as the locking sleeve. So all of these are balanced in one assembly. But as before, we remove material from the locking sleeve and from the shaft sleeve. There are now 2 sealing stages and 2 sets of assemblies for the primary rings. So these primary rings, which are designed in the same way, have slight differences in dimensions. And so this mating ring and this primary ring combination are kept together as a pair. And we don't mix over inboard and outboard sealing stages. The diameter, the balance diameter here and the balance diameter here is virtually the same. So when we're doing our assembly and our manufacturing of our dry gas seal, we ensure that the operation of these 2 and these 2 are correct. Now, along with the dry gas seal, there's also the separation seal. It's often seen as the poor relation of the dry gas seal because it doesn't have any spiral grooves. And there are various different types. Here we can see we're using a double labyrinth, which is the traditional method of a separation seal. It's located between the dry gas seal and the bearings, and it's being continuously supplied by a separation gas, typically nitrogen. This nitrogen is being continuously supplied before you start the lube oil pumps, before you start the compressor, whilst it's in operation, and after you've shut down, and after you've shut down the lube oil pumps. It's been supplied with nitrogen at a very low pressure, but has a very high flow rate. The flow of gas is in 2 directions. Firstly, it goes off towards the bearings to prevent any lube oil from the bearings from going into the dry gas seal, where it can cause issues of damage and hang-up. But it also goes off in the other direction, preventing the leakage of the dry gas seal from going to the bearings. And so there would be equal leakage going off in both sides. On the seal side, the leakage goes up the secondary vent. So the secondary vent would be a mixture of the separation gas leakage and the outboard seal leakage. But this is not the only type available. There are also seals available with carbon rings. These carbon rings that you can see in blue here are in segments and they're sprung loaded. This is a contacting seal, but operates very similar to that of a double labyrinth. Again, it's been supplied with a separation gas, again nitrogen, but at a higher pressure, and the amount of leakage in both directions is now greatly reduced. It's still preventing a migration of oil into the dry gas seal and leakage of the dry gas seal to the bearings, but is working with a much lower flow rate and therefore lower consumption. If you look further to the right, you can see that we've made an alteration, an addition, and this addition is to have a labyrinth between the 2 seal stages. We also have another port and another injection point. This seal is a tandem seal. It's still a type 28AT, but now it has an intermediate labyrinth and it's used for safety purposes. The inboard seal is operating the same way as we've seen before, but now all of the leakage will go up the primary vent. In order for this to happen, a secondary seal gas supply, normally quite low, 2, 3, maybe 4 bar, is applied, and the leakage goes through the labyrinth and out through the primary vent. So the primary vent is a mixture of the two gases. The remainder of the secondary seal gas will go through the outboard stage and then go out through the secondary vent, where it may or may not be measured. This system is pretty much the common type of dry gas seal supplied today. It can be used in a number of different applications, both onshore and offshore. Just referring back to the separation seal, we have different types. Originally, John Crane produced the Type 82, and that was superseded and replaced by the Type 83, although there are some Type 82s still in the field. The Type 83 has two noticeably different designs of carbon rings. The inboard stage has holes running through, whereas the outboard only has these slots. The gas is applied between the two, and there is sealing at 3 positions, here, here, and here. This is a contacting seal, and so there is a bedding in period where these panels are actually rubbing against the sleeve. The carbon rings themselves are static, and the sleeve is rotating. So that's a contacting seal, but there also is available a non-contacting seal. It's called the Type 93 FR, and FR standing for floating ring. So the carbons will actually float above the surface of the sleeve. This is at a smaller dimension than a double labyrinth, and so the actual consumption rate again is reduced, but not as much reduced as that with a contacting seal. It's up to the customer which option they wish to go for, double labyrinth, contacting, or non-contacting separation seal. Now, as I said, pressures have been forever increasing, and we had a problem with pressure once we reached a certain condition. So we had to redesign the dry gas seal to cope with the higher pressure demands. And it meant changing this area around the back of the primary ring. As you can see now, the retainer is now being modified and has a polymer ring and a carrier design. We've actually replaced all of the O-rings on this seal with polymer rings, polymer seals. These are made of PTFE and have advantages over the traditional O-ring seals. The balance diameter is now this sliding diameter of this carrier, so the carrier moves back and forth. And so the fit of this polymer seal is very critical. If it's too loose, then the gas can blow past. If it's too tight, then it restricts the free movement. Now, polymer rings are made of PTFE, and inside there is a spring. The way they operate is that the gas is applied into the spring. It becomes energized, and so the higher the pressure, the better the sealing. We now, by using this design, can go up to 180 bar dynamic. And most applications these days fall in this region, up to 180 bar. If we look at the seal itself in section, we can see more clearly there is a distinct direction that the way the polymers have to be installed. The gas has to go into the spring so that these two lips can actually open up. If there is a high pressure coming in the other direction, it will just blow straight past. However, the API 692 do state a figure for how much reverse pressurization statically, stress statically, the seal can withstand, and it's 3 bar. Ideally, of course, we don't want reverse pressurization, statically or otherwise. So we have our seal. There is our carrier, clearly visible, and our polymer seals. Now, with the introduction of re-injection, then it exceeded even the limits of an XP seal. So we had to redesign the seal once again. This time we introduced the Type 28 EXP for extreme extra pressure. And we used a system referred to as an ADC, an active deflection control. It's a little sub-assembly that you can see in this area here, and is to prevent extrusion. Now we can raise the pressure capability of the seal up to 425 bars dynamic, although we have done higher in test. This type of seal is used purely for the re-injection process. And if we look more clearly at this ADC, we can see how it's actually constructed. It can be made of 2 pieces or 3 pieces. On the screen, we have a 3-piece ADC made up of the polymer, which is in contact with a coated surface of tungsten carbide. There is the spring. There is a backup ring made from a special polymer composite, and also another polymer composite used as a support ring. Note there's a small gap here. Once the seal is under pressure, this support ring will distort. It will come down and close up this gap, thereby preventing any extrusion. This backup ring is also to prevent extrusion in this direction. So if we look at the ADC, once it's inside the retainer, we can see very clearly the white of the polymer ring with the spring, the black of the backup ring, and the plate. And this plate holds it all in position. You can see from this upper photo, there are screws. And these screws are glued into position to make sure that it's not going to be tampered with. So the fit of the polymer seal and the carrier, as I said, is very, very critical, and is one of the operations we carry out as part of our production process. So until recently, there have been 3 designs of dry gas seals. The Type 28AT, which is a unidirectional seal using O-rings, has now been largely down to high-speed, small seals at a low pressure. The Type 28BD is the bidirectional version with the Christmas tree design of groove. The Type 28XP is used in this area here, which is where our core business lies. It's unidirectional, using polymers and using carriers. The 28XP-BD is the bidirectional version of it. The XP can also be used in LNG duties. As you can see, these are very large seals with very large shaft diameters, but generally very low pressures. These are the biggest seals we've ever manufactured and are used around the world on LNG sites. The third seal, or main seal, that we've provided is the Type 28EXP for the re-injection duties that you can see in green here. Although the graph stops at 350 bar pressure, then it can go higher. And we have experiences of higher pressure seals than that. But you can see there's a bit of a dead area around here, which has no seal supplied for it. We can supply seals in this area, but they would be what we refer to as engineered seals. They'd be special seals with special design features which would cope with the large diameter, higher pressures. Now, there's also a new range of dry gas seals, all based on the design of the XP seal, and these are referred to as Aura. And the Aura seals were first introduced in 2014, and it was this yellow seal here at the upper range of the XPs. This is the Aura 220, the number 220 referring to the maximum pressure. The Aura 180 was introduced a year later, and the Aura 100 is also available. The Aura 425 is still in development. Now, these seals, which look like they're similar in positioning to the ATs and XPs, are not to replace the existing seals. These are to be recommended on new projects, or if there's been damage to a seal beyond repair, we will recommend an Aura seal is used in its place. So the idea of the Aura seal is not to replace all the ATs and XPs around the world. It's more standardized. It's more of a standardized seal which now meets the API 692 standard. Here you can see the Aura 220, and it has a lot of similarities with the XP design by using the carrier system here and polymers. We've also taken other designs from other seals we've had in the past and put them all together, and that was the Aura standardization program. But we've now introduced a narrower section seal, the Aura 120 NS. This has been introduced for pipeline retrofits. So the seal can be used as a retrofit to existing systems without a lot of machining necessary to the casing or to the shaft. It's reduced in size, radially and also axially. So it is a very small, compact seal and has been available for the past few years. Now, along with the dry gas seals, there's also the control system. Dry gas seal is being controlled and monitored by the control system, and these control systems can get very complex. As you can see from the photo here, we have a dry gas seal panel retrofit for a Rolls-Royce compressor system for PetroChina. The system is a control and monitoring system featuring filtration, but it also has a gas conditioning unit. And the gas conditioning unit is to give the correct quality of gas, both pressure and temperature. So it has a booster to boost the pressure to give the correct differential pressure, and also a heater to make sure the gas is at the correct temperature. If the temperature of the gas drops too low, then liquids can drop out of the gas, referred to as condensate. So the temperature of the gas needs to be kept high. So we'll look at these various different stages now. Now, on a dry gas seal system, there are key elements, and control systems can be supplied in 3 different ways. From the compressor manufacturer, from the seal manufacturer, including John Crane, or a third party. Whoever supplies the system will supply either a flow control system, or a pressure control system, or a mixture of flow and pressure. Here you can see we have various different elements necessary for any control system. On the seal gas supply, we have a filter or a filter unit. This is to give the correct amount of cleanliness to the gas. If you remember, the gap between the mating ring and the primary ring is about 3 microns. So the filtration traditionally has been 3 microns. API 692, which has just been introduced, now states that the filtration should be 1 micron, which means that the filters will not last as long, but will take out more of the particles. After filtration, it goes through control and measuring. It can either be pressure controlled or flow controlled. Some manufacturers favor one over another. At the end of the day, it's up to the customer which system they wish to use. The gas, after being controlled and measured, is injected into the seal at this point. As we've already mentioned, most of the gas, probably 90% of it, goes back inside the compressor to keep the dirty gas away from the gas seal. The remaining 10% goes through the gas seal and out through the primary vent, where it gets measured and then leads off, in this case, to the flare. Now you can see that we have our labyrinth between our 2 stages. So we need our secondary seal gas supply and a separate filter unit. So these filters that you can see here are actually separate units, not the same one. This filter would be of the same size, 3 microns or 1 micron if it's to the latest standard, and then it would be controlled and measured as it's injected into this position here. As we've already mentioned, the gas goes through the labyrinth and out through the primary vent, or it goes through the seal and out through the secondary vent where it may or may not be measured. So the control system has to feature all of these devices. In addition, there needs to be alarms, trip facilities, so if anything does go wrong with a seal or potentially goes wrong with a seal, it can be detected by the local panel, such as a panel you can see on the left-hand side here, or in the control room. This panel that you can see on the left-hand side has the 2 distinct filter units. one for the seal gas and one for the separation gas and/or the buffer gas. Now, it's not one system or interrelated. They're all separate systems on the same frame. So firstly, we have the seal gas supply with the filtration. We have the primary seal leakage, the buffer gas injection, the secondary seal vent, and the separation gas. All of these are required for this type of seal when they have an intermediate labyrinth. If there wasn't an intermediate labyrinth, you'd have a seal gas, primary leakage, secondary vent, and a separation gas. So if we look at these mini systems, we can see we have our supply. And the supply of the gas typically comes from discharge pipework, but not always. Sometimes it could be the second impeller, third impeller, whichever case, it's higher than suction. So both dry gas seals, both the drive end and non-drive end, work above a suction pressure, maybe a bar or 2 bar above that pressure level. On this example, we have a pressure differential control valve. So it's controlling the difference of pressure between a reference from the compressor casing or from a balancing line and is able to adjust to give the correct difference. We also have the filtration unit, which has 2 filters, one active and one on standby. We have flow meters, so we can see the flow going to both seals, both the drive end and the non-drive end. Filter units are, as you can see from here, are made, in this case, from duplex. Duplex is corrosion resistant, and so it's suitable for all applications. Inside these 2 chambers, we have the filter elements. As I mentioned, one is active and one is on standby. Now, as the compressor is running and the gas is passing through the filters, then they become gradually more and more dirty. They become more blocked. And so, by measuring the pressure before and after, we get a differential pressure. Once this reaches a level of, say, half a bar, then we need to change over from one filter to the other. But this can be done whilst you're in operation. You don't need to shut down or depressurize. By opening up this equalizing valve and turning this handle, you can transfer from one filter to the other. Then by closing off this valve, you've isolated the dirty filter element so it can be removed and replaced by maintenance. Then the replaced filter element becomes the new filter. Depending on how dirty the gas is, these may last for several months. And on some sites, there may be a requirement to change the filters every 6 months, whatever the condition of the filters. The filters themselves can vary in design. They may just remove particles, in which case the gas comes into the center of the filter and then goes through this filtration stage. Here you can see it's this pleated design to give maximum surface area of filtration, and it goes from inside to outside. Any particles that are 3 microns or larger will then be trapped, or if it was a 1 micron filter, anything large, smaller than 1 micron that would be allowed through. Anything 1 micron or larger would be stopped. But there are also methods of reducing the amount of liquids. Coalescing filters have a coalescing layer and a drain layer to separate the liquid from the gas. The liquid is heavier than the gas, and so it will drop out by gravity. Again, it goes from the inside to the outside. And there are also filters which remove both particles and liquids. So if we go to our primary sealing stage, we can see that we have a very simple arrangement here. It can be much more complicated, but here we have a leakage block with an orifice plate. We measure the pressure before and after the orifice plate, and if there are any problems, it will be checked by this pressure transmitter. We also have flow meters indicating the amount of flow passing through the primary vents, and also check valves. The check valves are necessary to prevent back pressurization or reverse pressurization of the flare pressure on the seal. So it's necessary to have these so the movement of the gas is always in this positive direction. At this point, both leakages come back together and go off to a common flare line. Now, if your seal has an intermediate labyrinth, then it will require a secondary seal gas supply. It may, however, be that there isn't a labyrinth, but no need for a separation gas supply. But there is a provision for it if there is a problem or if the actual gas composition changes, it can be connected up and used. We have our separate filter unit, designed in the same way as the primary seal gas supply. The nitrogen will come in, go into one of the filters as before, and then it would be divided up into the two separate supplies to the dry vent seal and the non-dry vent. And we're measuring using the flow meters. This filter unit may also be used for the separation gas, because the separation gas and the secondary seal gas may be the same, but working at different pressures. In this case, the gas would come out of the filter and then be regulated to the correct value. Once it's set, then it needs to be locked in position so it can't be tampered with. And both seals are then supplied with this separation gas at a very low pressure. Now, I mentioned about the requirements for the gas, pressure and temperature being very, very critical. It may be necessary to use a heater, and this heater will be used on the standby, startup, and the shutdown condition. That's because when the compressor shuts down, the temperature of the gas will actually drop. Now, if it drops to a certain point, it's referred to as the dew point. The dew point is when liquids will start to form and start to drop out of the gas. And this could be damaging to the dry gas seal. And so we need to have some kind of a heater element. So when the seals, when the temperature comes down, the heater starts to heat the gas. This is one method that can be used. Other methods are to use warm nitrogen or to use fuel gas as your startup gas. Once the compressor is running and heat has been generated, then the gas from the discharge is sufficient to be used as our seal gas. And so the heater is on standby until it shuts down and the temperature drops again. So the gas conditioning unit is in addition to the control and monitoring system. It's a bolt-on item and can be bolted onto the existing system, the standby condition. It's delivering clean seal gas at the correct pressure, and we can supply up to pressures of 204 bar and temperatures of up to 135 degrees C. It improves your seal reliability and increases your seal life. And seal life is something that's going through a bit of a change recently. Traditionally, we've said that seals can run for 5 years continuous running before they need to be replaced. Now, with the advent and success of polymer seals, this is now pushing to 7 years, 8 years, or even longer. It's used to eliminate any contaminated products and can help with the actual maintenance program. It reduces on space requirements and has cost savings as well. And as I said, it's a bolt-on to an existing panel. It can be fabricated to the API standards. So the API 692, which I mentioned, is for dry gas seals, control and monitoring systems, but also gas conditioning units as well, and separation seals. It can be designed and manufactured to a customer specification, so you can have it made for your own particular purpose. And there's a worldwide service capability that we can provide for both the dry gas seals and systems. So if there is a problem at all and you need service assistance, then we have a number of service centers around the world. This is where your dry gas seals would go back for refurbishment and retesting, and there would be service engineers available within a very short space of time. So that just shows you a slight introduction into dry gas seals. As I said, we do longer duration courses at our various different training centres. You can find out more details about these training centres by going on the John Crane website. As I said a little bit earlier, there is actually a follow-up course to this one, which is on dry gas seal failure. And by going back to the John Crane portal, which we recommend you do, to fill out a feedback questionnaire to receive a certificate, there is more detail about the other dry gas seal course and all the other courses which are being presented. Thank you all for attending. I hope it was interesting, and look forward to seeing you either on another of these online sessions or at one of our classroom sessions, which, as I say, you can access from the John Crane website.